I will begin with a word of prayer. Heavenly Father, we thank you for your creation. Again, we thank you for this day and you students. Just ask you just be glorified in what we do this day, Lord, and help us to understand a little bit more about Gauss's law. In your name I pray, Lord Jesus. Amen. Oh, here's the paper attendance sheet. So if you're here, there you go. So I hope I have everybody's homework up here. Looks like I do. 1, 2, 3, 4, 5, 6, 7, 8. Well, maybe. I see I need to close that door. Let's see here.
Too late for this year, but
so Gauss's law relates the electric flux to the charge. And Gauss's law is stated simply as follows. It says that the charge enclosed divided by epsilon naught is equal to the flux, the electric flux. In other words, it's the integral of E dot dA over, whatever surface we have in mind. So Gauss's law is applied to a closed surface. This is not a physical surface, this is like a mathematical surface, right? It doesn't actually have to literally be, there doesn't have to be anything there. It's like a mathematical surface, all right? And so inside that surface, we have a particular charge which is enclosed, and Gauss's law says that the charge enclosed divided by epsilon naught is equal to the flux, all right? And so this is a basic physical law, and so we can apply it and see what we can derive from this, all right? So example 1, most simple example you can think about, just put a charge, let's say at the origin, right? And then we can just imagine encircling that with a so-called Gaussian sphere, right? Sphere, radius R, with Q at the center, right? Then, because the electric field points radially outward from the charge, right? And because there's a perfect symmetry of this sphere, because the charge is exactly at the center of the sphere, that means we can kind of like picture the electric field lines, right? They're going like this, yeah? Every different which way out of here, right? But the key thing about them is that, they what? They're all going out from the, the center point, and what can you say about them as they relate to the sphere? They're exactly aligned with the normal, right? So the electric flux here, the flux is simply equal to the magnitude of the electric field times the area, right? Which in this case is 4 pi r squared. That's the surface area of a sphere of radius r. So 4 pi r squared times the magnitude of the electric field, that gives me the flux. I'm saying that the flux can be calculated by symmetry, right? Because we know that there's nothing that distinguishes any point on the sphere. Therefore, it must have the same magnitude everywhere. So by that logic, the electric field's magnitude times the surface area should be equal to the flux. But then Gauss's law says it's equal to the charge enclosed divided by epsilon naught. What is the charge enclosed? Well, the charge enclosed here is just Q. Yeah? And then what does this give us? Well, this gives us that the electric field, due to a point charge, is Q over 4 pi epsilon naught r squared. There you go. That is the magnitude of an electric field, a distance r away from it. We've seen this before, right? This is the formula for the magnitude of the Coulomb field. So what I'm showing you right now, example 1, is that Gauss's law implies Coulomb's law in this sense. Any questions?
What is the subscript beyond the flux?
Electric flux. Later we'll talk about magnetic flux, which would be like this. So more towards the later part of the course, we'll talk about the magnetic flux, which is also important for like Ampere's law or Faraday's law. But for now, I will erase that. one kind of flux at a time in here, all right? So, yeah. Any questions? You're like, I already knew E was equal to Q over 4 pi epsilon naught R squared for this, so this isn't really that exciting. I mean, fair enough. What would the electric field be if instead of having a point charge at the middle, imagine we had like a homogeneous sphere of charge Q, right? So example 2, let us suppose we have, charge Q uniformly distributed over solid sphere of radius, let's say big R, right? Now, perhaps here, let me go back, if you guys don't mind me. Let me just fix this over here, because otherwise it's going to end up confusing some of you, possibly. So let me just, for editorial reasons, let's change this to a little r. 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 There. As to ensure that there's no confusion about the big R in the next example. This little r is a variable. It can be anything positive, right? If you said that the radius is like -2 meters, I'd be like, shut up. You're a mathematician. Get out. We do allow like negative radius in calculus 2 for like polar graphing, but that's a weird idea. And that whole angle flipping thing, that only happens in calculus 2 as far as I can tell. But Desmos does do that anyway. Like if you put in Desmos like r equal to -1, it's going to give you a circle. Okay, so anyway, proof of legitimacy by software, I guess. It's a method of proof. But so charge Q uniformly distributed over a solid sphere. So let me draw a picture here, and I'll draw it 2-dimensionally. So what I'm saying is, I've got this, solid sphere. Maybe I should make this sphere bigger. My bad. We'll make it bigger. All right, so we got a sphere, all right, and its radius is r, right? And the charge Q is uniformly distributed out, smooth over the sphere, right? So I guess one of the questions I might ask you is, what's the charge density? Like, how much charge per unit volume are we looking at? So we're going to need to know that. Let's figure that out. So the charge density rho is equal to dq dv, right? But it's uniformly distributed. We can also set the infinitesimal rate of change equal to the average, like, ratio of the total charge, which is q. What's the total volume of the sphere of radius r?
4/3 pi r squared.
4/3 pi. Yeah, 4/3 pi r cubed. There you go. So there you go. That's the charge density. Great. All right. So there's 2 different cases we can think about, right? So let me think about like 2 cases. So case 1. and that would be little r greater than or equal to big R, right? If I think about a Gaussian sphere, which I'll illustrate by this circle, but understand this is a sphere. It goes, I'm just drawing a circular representation of the sphere because it's a good way to draw the picture. So if that radius, if the Gaussian sphere, right, is out to here, if this is R, if R is greater than R, then the charge enclosed is equal to Q for, the sphere of radius R, right? So then we're straight back to example 1, right? We're straight back to example 1 because there's the perfect spherical symmetry here again. So the flux is what? So we've got Q over epsilon naught equals to the magnitude of the electric field times 4 pi r squared. Therefore, the electric field is simply Q over 4 pi epsilon naught r squared. There you go. That's the formula for the magnitude of the electric field if we're outside of the charged sphere, or even right at the surface of it. Do we agree? I hope we agree. It's pretty much the same as example 1, right? Now where it gets interesting is case 2, right? Case 2. There's only 2 cases for this one, right? Which is that you have 0 less than or equal to R less than, we could even throw equals to R into this case as well, So I'm saying, suppose that we're looking at a Gaussian sphere, an imaginal, that's not a word, imaginary, mathematical sphere that's inside the charged sphere. So, like here maybe. And I usually draw the Gaussian spheres as dotted. I'm sorry I didn't do that for the purple one. Let me fix it. All right. Anyway. Now, technically, I would like to shade things, but whiteboards are just miserable for shading. But, I mean to, if you didn't understand, I'm saying that this whole thing, right, has charge in it. Oops, I'm smearing my markers. So now I've ruined my picture. Oh well. That's why we should use chalkboards. But anyway, Dr. Sprano and I have a plan. We're gonna secure some chalkboards, at least for the Spranex. Do you guys know what the Spranex is?
The Spranex is getting a chalkboard?
That's what we want. Maybe a pair. The Spranex is the offical next to Dr. Sprano's offical. You might wonder what an offical is. That's a office, that's a cubicle. It also sounds awful because they are. So, like, once upon a time we had actual offices with like walls and stuff and like a door and a roof. So if we imagine this Gaussian sphere, radius little r less than or equal to the big R, right, inside the charged sphere. So again, there's a perfect spherical symmetry, right? So the electric field must be pointing outward, just like before, all right? So the flux is still going to be the magnitude of the electric field times the radius. So we got charge enclosed divided by epsilon naught. It's still going to be equal to the electric flux, but in this case, it's still the case that it's the electric field times 4 pi r squared. You might wonder, do we ever get to the point of having an example where that's not the formula for the flux? The answer is yes, just not yet. What's the charge enclosed? Well, see, that's now an interesting question, because it's not Q, right? It's just a portion of Q. How do you find out how much charge is enclosed? So if we have a uniform charge density, what we can do is simply take the charge per unit volume times the volume, and that gives me the charge enclosed. So the charge per unit volume is the density. So I've got my Q over 4 thirds, I can't write, Q over 4/3 pi r cubed, that's my charge per unit volume. I wrote a square there, that's one of your fault. Let's see here, 4/3 pi r cubed, and then times the volume. What is the volume inside the red? Like, what's the volume here? What's that? It involves little r, yeah. How about 4/3 pi little r cubed, right? So that is a formula for the charge enclosed. Does that make sense? I hope it makes sense. I'm saying the charge per unit volume is the density. Density times volume gives you the charge. This assumes, of course, that the charge is uniform, right? If the charge was not uniform, we would have to use calculus. And of course, we still got the 1 over epsilon naught. It's there. And that's equal to 4 pi r squared times the electric field. The 4/3 pi's, they'd be canceling, right? Solve for the electric field, what you got? We got a Q, and we got a r cubed divided by, looks like a 4 pi little r squared times big R cubed epsilon naught by algebra. So I canceled the 4/3 and the pi's, right? And then I solve for E by dividing by little 4 pi r squared. I think that's right. All right? Can we simplify that? I think we can simplify that a little bit, right? What do we get? Therefore, the electric field in this situation is Q times R divided by 4 pi epsilon naught big R cubed. There's a different formula inside and outside of the charged sphere. It's probably helpful and interesting to graph. Let's graph the formula that we found. So what's going on? I'll put it right here. If we plot the electric field magnitude this way and the radius that away, what happens? What's the, I'll put the radius here for the sake of reference. So what's the electric field at the center? It's 0. Does that make sense? Because you've got an equal amount of charge every different which way, and it's all pointing towards the electric field would be pointing towards the center from all those different charges, but they're equal and opposite in all possible directions, so they cancel out at 0. So the electric field 0 at the middle, and it's largest where? What happens when you plug in? Notice that when these agree, right? I can't spell agree. This is not good. Somebody spell agree for me. A-G-R-E. It just looks wrong to me right now. Isn't that annoying? All right, so these agree. Think of that like pirate meme. So, for those who know. So if we set little r equal to big R, then these formulas match up. They should, right? When you have different cases, the cases should meet in a meaningful way, right? Unless there's something like divergent about the point where they meet. It could happen, like if you have a finite amount of charge accumulated at like a mathematical point, that's going to be a place where the electric field's not defined. Like a point charge. What's the electric field? In example 1, what's the electric field at r equal to 0? Oops, right? It's infinite. Is the electric field really infinite at the origin there? Or is that a mathematical idealization? Like, how big is charge? Should we view charge in the way of example 2? Is charge actually macroscopic? Is it spread out, right? Or is it actually point-like? Let me put a finer point on this question. How big is an electron? Very small. No one really knows. So for all intents and purposes, electrons are point-like. But it comforts me to think of the electron as not actually a point. It's actually kind of some small thing that's smeared out. It's just so small we can't actually ascertain its actual size. All right? In some sense or another, these questions break down because they involve quantum mechanics, which is what happens when we look at things very small. But another way to look at this is, it's more of a philosophical question than a physical one, but whether or not there really are point charges. You could always think about every point charge as being like one of these, where the electric field isn't really divergent at 0. It's just that there's like a little charge that the electric field goes to 0 inside the charge. And it's just that the Coulomb field outside of the charge, not actually inside the charge. It continuously drops to 0 like this. This much I think everybody probably agrees on. There's not actually an infinite electric field at 0. That's a mathematical artifact, most likely. Nevertheless, there is a formalism which formally puts an infinity where charges are. It's called the Dirac delta function, which we'll talk about in differential equations eventually, towards the end of the Laplace transform chapter, if you take it with me. So the electric field's linear. It just increases linearly with this slope of q over 4 pi epsilon naught big R cubed, right up until it gets to the value of q over 4 pi epsilon naught big R squared, and then it drops off like an inverse, like this, right? It drops off like an inverse square, a reciprocal, like that. So the largest the electric field is in example 2 is at little r equal to big R. And then it goes to 0 as we go to infinity. Any questions? Okay, well, good. Here's another one that we like to ask you guys. So symmetry is an important idea in this particular story arc of the course. Like, symmetry solves a lot of your problems, which I guess is a welcome break from integration, right? This stuff was all predicated upon some ugly integrals that you're scared I might make as part of the course, but you should just call me Mr. Cook in here. I'm not a doctor. I only have a master's in physics, so I'm like a Mr. Cook here, Unless I do Calc 3, then you can call me doctor. So, I don't know. Depends on the day, I suppose. Example 3. Imagine we have a cube. All right? You got it? There's a cube. We'll say side length L. All right? And suppose I put a charge Q right here. All right? My question is the following. What is the flux through the top face? Of the cube. I'll even shade it for you with this. Well, this might be, I don't know. It's okay, it's okay. So, what do you guys think? How should we do this? Yeah?
Is it going to involve like the area of the cube?
Sorta. in some sense. Let me draw a suggestive picture. Like, what if we envision that particular face as, like, let's say, this right here. All right? So like this point of reference is this point of reference. I'll call it Bob. Bob be there. All right. And this is a bigger cube, right? So my original cube is, it would take how many? 8 of these to make this thing. So I don't know if my picture is quite right to scale. I probably should make it more like that. Maybe that. I don't know. I'm trying, guys. I'm trying. All right. So like inside here, my picture's probably breaking down, but my point is, maybe it'll help. Let me draw a top-down view. Top-down view. Top-down view. All right. So here's where the original cube was, right? So the Q is right here. All right, top down. So my point is, if you can understand my picture well enough, this is at the center of the large cube, right? The large cube is what? It's 2L by 2L, right? Each side length is 2L. 2L times 2L times 2L is 8L cubed. Like I said, it takes 8L cubes to make the big one. But the point is that the little q is at the center. So what does that give you guys any ideas? Yeah? It's, well, yeah, that's the question, is the flux from Q uniform, right? Which field are we talking about? The only charge here is this charge Q, right? So it's the Coulomb field. How does the Coulomb field work? It is the same in every direction, right? So how much of the Coulomb field flux goes through the top face of the big cube? The same as the bottom, and the side, and the side, and the side. There's 6 faces, right? So 1/6 of the total flux in the big cube must go through the top face of the big cube, right? And that's 1/4 of that face, right? So that means that it would take 24 of these little squares to cover the surface area of the big cube, right? So since it's symmetrical, that means that 1/24 of the flux must go through there. So that's it. The charge enclosed divided by epsilon naught, you know, that gives us the flux through the, or this is the flux through the whole, you know, for the big cube, right? And so that tells me that the flux through the face, the upper face, top face, is equal to Q divided by 24 epsilon naught. Would you like to see the integral you'd have to do to calculate that? You would? Okay. That was a rhetorical question, but thank you. So this is what not to do. Something's got to go. This one. So let's see here. If I put Q at the origin, then this right here would be like Z equal to L. And we have something like, I guess, man, X is negative and Y is negative. So it's something like minus L less than or equal to X less than or equal to 0. Minus L less than or equal to Y less than or equal to 0. That describes the upper face. And so the area element there would be dx, dy, And the unit normal here points like a so, right? So that's just a z hat. And so if I calculate the flux directly, integral top face. So I have to integrate from minus L to 0, integrate from minus L to 0. What's the electric field there? So the electric field due to a point charge, the Coulomb field, we know that. It is Q over 4 pi epsilon naught. And we can do r vector over r cubed, which in this case is Q over 4 pi epsilon naught. We've got x, we got y, our z is equal to L. And then we've got x squared plus y squared plus L squared to the 3/2 power downstairs. So yeah, we just need to do that. So Q x comma y comma L divided by 4 pi epsilon naught x squared plus y squared plus L squared to the 3/2 power. That gets dot producted with dx, dy, and z hat is just 0, 0, 1. So you'd actually just end up integrating L divided by the 4 pi epsilon naught times x squared plus y squared plus L squared to the 3/2 power over these ranges. And apparently that works out to Q over 24 epsilon naught. Obviously, this is the wrong way to do this problem, right? Yeah. I made my point, I think. Yeah. So that's one of the first points of order on the test is you got to decide what's the right tool for the job, right? If your question is to find the electric field due to a rod of charge, a point a little bit beyond the rod, that's a problem about integration like we already did. There's no way to solve that problem with Gauss's law, as far as I know. All right? I don't know how to, that problem we did with the finite charge in a line, a little line segment, and then find the electric field a little bit point beyond. I do not know a way to do that problem with Gauss's law, personally. All right? There's no nice symmetry to that problem. On the other hand, a problem like this, or obviously the solid sphere problem, definitely Gauss's law is the way to go. Let me show you another example. Funny story, my brother is a mathematician. Well, I have two brothers. My little brother, Andrew, is not a mathematician. I mean, he's good at math. He could have been a mathematician, but he does other things. It's like a public school teacher. He does all kinds of stuff for them, like audio, video for their sports, and drives a bus and everything else. It's very hard to fire him. He's got his many, many things he does. All right, it's important. If you work in a public school, someplace where you're not from, you must put your tentacles into everything. Otherwise, they will fire you at some point for a friend. It's just true. Anyway, but my other little brother, Bill, was taking physics 2 at Bob Jones many moons ago. And so they were going along. They'd done Coulomb's law, the Coulomb force, all that stuff that we've done, right? Integration, the whole bit, And then the day before the test, the day before test 1, the teacher covered Gauss's law. And Bill thought, well, that's just one class. The test will mostly be on everything else, right? Wrong. Very wrong. We physics instructors, we love Gauss's law very, very much. And we think we're being generous to students when we test on it because it's easier than the other stuff, right? But it's only easier if you know it. And such is the story of how my brother almost earned a B in physics 2. So that hurt him. And then the rest of the semester, he's scrambling to get back points, But anyway. Where are we? Example 4. So Gauss's law matters. We love Gauss's law. It's super awesome. Here's another one. Imagine you have an infinite line charge with charge per unit length lambda. So this lambda is the charge per unit length, right? So I guess we could say that's like dq dz if you like, for the sake of discussion. If I make z say it's on the z-axis for the sake of specificity. All right. I kind of like the way my brother does physics, though. He'd be in like lab with his lab partner, and they'd be doing an experiment. And what my brother would do is he would calculate things as they went. So when his lab partner, Luke, was taking a measurement, Luke would be like, I think it's 3.2 centimeters. And my brother would be like, I think really, if you look again, it's more like 3.18. Somehow their error always came out just where it needed to be. So now Professor Dromby does not like this story, but I personally, I like it. I don't know. Like lab equipment that you guys use in the undergraduate labs, it's very sketchy, right? I don't know, but sometimes. So this is an infinite line charge. They're kind of hard to find, but this is an idealization, right? So imagine you have a line of charge that's so long that we can't really, it just goes on and on for all intents and purposes, all right? What's the electric field due to this infinite line charge? What happens? It should do what? If I look at this line charge like dead on, like this, right? And suppose it's coming out at you. The electric field should be like this in all directions, right? It should be something like this. It should go radially out from the charge, right? So this is like, you know, looking head on the wire. I can't spell wire. That's not a good sign. All right. This problem you could try to do with integration to find the electric field at a particular point off the line, but let's not do that, as it would require an improper integral. And yeah, but by symmetry we could argue, like, you know. So the question is, we want to know, like, what's the electric field like here? So my first point to you is that by the symmetry of the problem, I can see that the electric field should be something like the magnitude times what I call r hat. Oh man, I guess I call it s hat in this class. I'm sorry, guys. So this, you know, this is points radially away from z-axis. I can give you a formula for it if you'd like. Like, let me just, let me not, because we don't need all that. I don't want to write things that you don't actually use. I mean, my point here mainly is that it can only have a radial dependence, right? Because it can't depend on z, because it's infinitely long. So there's no difference between, say, this point and that point. There cannot be a z dependence. To be clear, I'm putting this to be like the z-axis, which is also where the charge is. Yeah?
This may be dumb, but is the dots you put, that you're trying to find the electric field of,
Yeah.
is that also an infinite line, or is that just a dot?
Just a dot, just a point. We're trying to figure out what's the electric field at that point.
Cool.
So charge everywhere along the line. What's the field right there?
Okay.
So here's what we do. We imagine a Gaussian surface. Not a sphere this time. That's not the job. That's not the tool for this job. This one, you want to use a Gaussian cylinder. So Gaussian cylinder, like this. All right, so I'm saying that the line charge goes straight down the middle of the cylinder. All right. And we'll let the cylinder have height L, and let's it have radius, let's call it S, since I'm using S for the radius here. So what's the electric flux through the cylinder? You got the flux through the top, plus the flux through the side, the curved side, plus the flux through the base. Right? This is a based cylinder. Just saying. Well, if the electric field points radially outward, like let me hazard a picture of the electric field over here. To be clear, what I'm saying is the electric field has to go like this, right? I can't. You get the. I hope you get the idea. Like it's going out from the. Look at that. That is tangential to the top face and the bottom face, right? So the flux of the top and the bottom is 0. And the flux through the side is the magnitude times the area of the side, right? So the magnitude we call E, the area of the side, 2 pi s times L. 2 pi SL. That is the area of the cylinder if you lay it flat, right? Do we agree? Disagree? I hope you agree. Now we just have to figure out what's the charge enclosed and divided by epsilon naught. Gauss's law says that this must be equal to charge enclosed divided by epsilon naught. What is the charge enclosed here, though? And we're talking about, it would be this part, right? The charge is like here, right? Yeah?
Quick question, when it comes back to that equation, why is the S not squared? Like, normal equation?
What's the area of the side of a cylinder, right? So imagine, just take the cylinder, like cut it somewhere, right? If you laid that out flat, this length would be 2 pi s, because that's the circumference, right? And the height would be L. So 2 pi s times L is the area of the side if we just take it and lay it. Yeah, just area. Flux is about area and magnitude. That's okay. So then, what's the charge enclosed? Well, we take the charge per unit length, which is defined to be lambda, times the length, which is, by our construction, L. Right? So the charge enclosed is simply equal to lambda times L. Because lambda is the change in charge per change in z, and this L is the change in z for our object. So like that gives you the change in charge, the total charge on that line segment. Density times length gives us charge enclosed. So in this case, Q enclosed is simply, what was I saying? Lambda L over epsilon naught. Now, finishing blow here, we just solve for E. And what do you get? We get E is lambda over 2 pi epsilon naught times S. And if you want me to put in the directionality, we could do that next. But there you go. That's the magnitude of the electric field due to infinite line charge. It drops off as the reciprocal of the distance from the axis to your field point. A formula for this we could write would be this also. So like it works out, E is equal to lambda over 2 pi epsilon naught S, S hat, like that. If you thirst for more equations, well, I'll tell you, I'll write some of that stuff at the start of next class. I think we're done for now. So, any questions?
Actually,
Yeah.
Where did the E come from?
Which E?
Times 2 pi s.
This is the flux of the side. Yeah. Is this. So it's, I mean, if you want me to, I could kind of do it like this. It's the flux is equal to the side is equal to the integral over the side of the electric field dot dA, right?
Yeah.
But that's equal to the electric field dot the integral of dA because the electric field is constant. Well, that's not quite true either. Let me not do that. That's just nonsense. But we could derive it with calculus, but I'm just using symmetry to write it down. I would like to do it with calculus. We could use calculus to do it. Do keep asking these questions because it motivates me in my calculus 3 digression like a week from now. Woohoo. Thank you. All right, that's it, guys.